Hi, this video is for Collingwood High School Advanced Topics in Math for the spring of 2020. You guys will recall that when we had our interruption and then there was spring break, just before that happening, we were going through part 3 of the cryptography notes. And so what I'm going to do in this short video is I am going to do the last page of that package of notes. So this is the last page of cryptography part 3. This is the full definition of the RSA Cryptosystem, and we'll do a small example of the RSA Cryptosystem. And then what I want you to do is choose 2 prime numbers, maybe in the roughly in between, maybe say between 100 and 300, so the whole thing doesn't become unmanageable. I want you to choose those 2 prime numbers, make a crypto system. I want you to encrypt something with your crypto system, and then when we meet up tomorrow, we'll trade around, and so we'll just partner up, and you will give one of your classmates your encrypted text, and then that person will attempt to figure out, knowing that it's RSA encryption and that you've used primes, say between 100 and 300, will attempt to decrypt. So we'll see that we'll be able to decrypt maybe with a certain amount of time, but we'll be able to decrypt because the prime numbers will be small. The security in the system rests in having the prime numbers large. And so we'll be able to, anyways, we'll be able to discuss some of those features tomorrow when we have our Zoom meeting. So go through this short video on the crypto system, design your own. Don't tell anybody what it is. Encrypt something short, like just encrypt a number. Okay, so because we can just easily translate text to a number. So encrypt some 4 or 5 digit number, and then we'll try to see if we can figure one another's out tomorrow morning. Okay, so let's make sure we know exactly how this crypto system works. We have a number n, which is the product of P and Q are primes. So the plain text, the ciphertext are all in Zn, where n is the product of 2 primes P and Q. And our key is going to be, well, no, let me not say it that way. Really what's secret is P and Q. P and Q are kept secret. The full excuse me, the full crypto system consists of N, P, Q, and then A and B. We're going to see how this works. A and B are the 2 exponents in the encryption and decryption function. Okay, here we go. So we're going to define the encryption function to be x to the b mod n, right there. And the decryption function will be y to the a mod n. Coming in the next lecture, we will prove that these functions, like these functions are inverses of one another, so that dk undoes what ek does. Okay, so first, let's just say a few things about this. There is right now the belief, but no proof, that this is a one-way function. Okay, belief that this is a one-way function. Okay, and then this decryption function, we call this the trapdoor. That this is what is allowing the person with the key to undo the encryption. So this is the trapdoor. And what does the trapdoor do? The trapdoor allows this. Because the person who initiates the code or devises the code knows what P and Q are, then of course they could easily compute n, and then because P and Q are prime, it's easy to calculate phi of n. Phi of n will simply be P minus 1 and multiplied by Q minus 1 because P and Q are prime. So then you could easily figure out what A is, because A is B to the minus 1 mod phi of n. Then you would do that via the extended Euclidean algorithm. This is gonna these next few lectures are gonna tie together nicely a lot of the number theory that we've been looking at. Okay, so maybe you see here immediately that in fact, if I didn't know P and Q, but I could calculate phi of n efficiently, then this also would not be secure. So the difficulty of factoring a large number n into its two prime factors is of equivalent difficulty as finding out phi of n. So either one of those, if either one of those problems were solved, then the security of the RSA would be defeated. Okay, so the key is in two pieces. N and B are the public key, and then the values P, Q, and A are the private key. So what you do when you're Amazon, you have P, Q, and A on your computer, and you don't tell anybody what those are. And then you publish N and B on well, you just give that to anybody who wants it. And then the person who's going to send you money uses N and B and the encryption function to encrypt their credit card. And then they send it to you, and only you can decrypt it because you need the P and the Q and the A to do the decryption. So it allows you to encrypt publicly. Everybody knows everybody knows the encryption function, and people in fact know what the decryption function is as well. But you you can't operate the decryption function because you don't have the numbers you need, and you can't get those numbers from the public key. Okay, so let us just take a look at a small example of the RSA crypto system where this is not secure, and it's not secure only because P and Q are going to be small, and they're going to be small because otherwise it's not practical for us to show you how to do it. But this is exactly how the thing works for in the larger scale case. The only difference is that the security rests on the prime numbers P and Q being much larger. This is not secure because you could just keep trying all the primes, and sooner or later you'd find the pair. So it would not take much computing time to figure out. Okay, so here's what happens. Bob, that's the person who is going to develop the code. Bob chooses, okay, so this is in our world, we've been talking about business application, but so the Bob would be Amazon. Bob chooses P is 101 and Q 103. Okay, P and Q are prime. That is key. They must be prime. Okay, then he multiplies them together. So that's 101 multiplied by 113. Oh, I changed. Sorry. 103 is prime, but I want to use 113 because that's what I used below. So let's use up P is 101 and Q is 113. Multiplies them together, and he gets this number here, 11413. Okay. Then he computes phi of n, and that is phi of 101 multiplied by phi of 113. We recall that phi, the Euler-Toten function, is a multiplicative function. Okay, so that would be 100 times 112. Okay, because phi of p is p minus 1 when p is prime. And then that is 11200. Okay, so this number here is phi of 11413. Okay, now I want you to imagine that you didn't know 101 and 113 and think of how difficult it would be to compute phi of this number. Okay, you don't have a strategy outside of factoring. That's the whole issue. And factoring, of course, means basically getting back to what is P and Q. Okay. All right, so I will just point out here, I'm going to factor this number. This is not typically done, so let me just, in practice, not done, but so we can see what's going on. In practice, this is not done, but I want to point out that 11200, if I were to factor that, this number here, 5n, that number factors in this manner here, 2 to the 6, 5 squared times 7. There it is. Okay, so we want to choose a number b. Okay, so we want to choose b so that the greatest common divisor of b and phi of n is 1. Okay, so that means it can't have any, it's not divisible by 2, 5, or 7 in this case, because I've factored, I can see that. Not divisible by 2, 5, or 7. Okay, what if I didn't want to factor 11200, which I don't? Well, how would I pick b? I would just randomly choose a b, and then I would run the Euclidean algorithm on b and phi of n and see if it came out to 1. If it didn't, I would just randomly pick another one. So I would not try to factor. It would not take too long until I stumbled onto a b that was relatively prime to phi of n. So that would be one way. Okay. So now Bob chooses a b. So suppose we'll pick one. There's many choices for b. You just need such that b has an inverse. So that's why we want that relative prime condition in place. So we suppose Bob chooses, what did I pick here? B equals 3, 5, 3, 3. Okay, then the inverse is computed via the extended Euclidean algorithm. Okay, so this is the inverse of b mod phi of n, and that number comes out to be 6597, and that is A. Okay, that is the secret decryption exponent. That right there is secret decryption exponent. Okay. The next thing that happens is that Bob publishes the public key. Bob publishes n at 11413. Okay, you don't know which 2 primes that's the product of, but you know that's the product of 2 primes. And he publishes b. That is 3533. Okay, so let's box this. This is the public key. Everybody gets to know that. So he publishes that in a directory. Oh, so anybody who wants to can look it up. All right. So Bob is the person, in our model that we always have. Bob is the person receiving the messages. Alice has some information she wants to send to Bob, and Oscar is looking in, right? Oscar's the bad guy. Okay, Alice now wants to encrypt a plain text, possibly say her credit card. Alice wants to encrypt plain text. Now I'm going to just use a number here, and I want you to do the same thing when you develop your example for tomorrow's class. I mean, this could just be some 4-letter word. So anyway, that's my plain text, or it can be a longer credit card number. But let's just not make these examples too long. Otherwise, the numbers get too big for us to sort of work with in a pseudo hand way. We want to be able to. We can use a calculator and such, but we don't want to make the thing so big that we have to run a lot of software to sort of see what's going on. So pick something fairly short for your plain text. So I've picked this for my plain text. 9726. So Alice wants to encrypt this to send to Bob. Okay, so what is she? Well, okay, that's the plain text. So obviously she has to encrypt it and then send him the ciphertext. So Alice computes 9726 to the 3533 mod 11413. Okay, so this is the plain text. Then this is here is B, and this is N. Okay, so that is has her plain text, and she's using both of those items of the public key. So she computes that, and in this example, that turns out to be this number right here, 5761, and that is the ciphertext. Okay, so then Alice sends Bob the ciphertext. "5761", and Bob decrypts. And how does Bob decrypt? He takes the ciphertext. This is Bob. He takes the ciphertext, 5761. He raises it to the power, which I have called A, 6597. That's the secret decryption key. Mod 11413. That's N. That's public. So this number right here cannot be found out by somebody, and also it cannot be computable from the public key. Otherwise, your security disappears. And when you make this calculation, you will see that you get back the plain text, which is of course what should happen. So this here is the ciphertext, and then this here is the plain text. This is the message that Alice wanted to send. So now let me just reiterate what I want you guys to do is do exactly the same exercise. Pick two primes, pick them between, let us just say between 50 and 250. So pick some primes, two primes between 50 and 250. Go through this entire exercise and then encrypt something, and be sitting there tomorrow morning with that system in front of you with something that's encrypted. And we will see if we can, using our computers and a sort of an exhaustive approach, we can see if we can figure out one another's plain text without actually having the private key. So we'll do that as an exercise to keep the prime small. Otherwise, this is going to be too difficult to do. Next thing, I just want to point to what's going to happen. I'm going to stop this video in a second, and then what will happen after this, we'll be moving on to the final section of the cryptography class. And this is going to include things like, well, we're going to start by proving that, in fact, here EK and DK in this RSA encryption algorithm are, in fact, inverse functions. We're going to do that. And then we're going to do some things like understanding how do we find large primes, and how do we think about what could be some type of attacks on the RSA crypto system. And in order to talk about these things, we are going to need a couple of major results from number theory. I think really they're completely fascinating of themselves, and that will be, in case you want to read ahead, we'll be talking about quadratic reciprocity. This was Gauss, and a major result in number theory. And then we will also talk about some technical details around that, the Legendre and the Jacobi symbols. I'll be back with another video shortly. Thanks, guys.